This is the Unit 6 review covering measurement, significant figures, dimensional analysis, mass, moles, atoms, percent composition, and empirical formulas. Anytime you're using a measuring device that has no moving parts, such as a ruler, you must estimate 1 decimal place past the smallest unit marking on that device. And so in looking at this ruler, the smallest unit markings would be these, and notice they are tenths of a centimeter. Therefore, we must estimate to the hundredths. And so in looking at this, I think everyone will notice that the segment that is listed, here's 6, here's 6.1, 6.2, it's not quite to 6.3. So if you measure this, everyone should have 6.2, and then that last digit is going to be the estimation. That's where you're going to have some variance in your answer. You know, you could say like 6.23 centimeters. You could say 6.22, 6.21. You know, which one's right? Well, they all are, because that last digit is an estimation. But the 6.2, you must have that portion. We have a similar situation with this problem. Graduated cylinder has no moving parts. The units should be labeled on their milliliters. As you will recall, when you read a graduated cylinder, you read the volume from the bottom of the meniscus. And so in looking at this, if I want to read where the bottom of the meniscus intersects the scale, there I've got 10, 11, 12, 13, 14, 15. The smallest unit markings is the 1 milliliter, and so therefore I must estimate to the tenths, and so everyone would have 15 point, and then that last digit is going to vary. You could say 15.2, 15.4, I don't care, but it has to have 15 point something. This is a classic analogy used to describe the difference between accuracy and precision. The main thing you have to recall, accuracy is how close a measurement is to its true or accepted value, where precision deals with the closeness of a group of measurements taken in the same way. It doesn't necessarily mean that it is correct, it just means that it is repeatable. An easy method to determine the number of significant digits in a measurement is what's known as the Atlantic-Pacific rule. If there is a decimal point present, notice present and Pacific both start with a P, you will start counting the digits from the Pacific side, from the left side, and go left to right, and you will start counting the digits once you reach the first non-zero. So in this example, it's present, let's go, okay, the 3 is the first one, 1, 0, 0, this one has 4 sig figs. In the second one, you will notice the decimal point is absent. There is no decimal point here, so we must use the Atlantic rule. Atlantic and absent both start with A. We're going to start from the right-hand side and move back left. So we're going to start counting when we hit the first non-zero. Okay, nothing, nothing. The 4 is the first one, and the 1 and the 3 also count. We have 3 sig figs in this example. To determine the number of significant figures in each measurement, we're going to apply the Atlantic-Pacific rule. And so in A, you'll notice it is present. We're going to start from the left-hand side. Neither 0 is going to count. The 4 and the 3 are both significant. This one has 2. For B, 107, there's no decimal point present, so it is absent. We're going to start from the Atlantic side. The 7, the 0, and the 1 are all significant. There are 3. In the next number, the 141.07 meters, there is a decimal. It is present. From the Pacific side, the 1, 4, 1, 0, and 7 are all significant. There are 5. 174 meters, it is absent. We're going to start from the right side going left. The 4, the 7, and the 1 are all significant. There are 3. 1.15 times 10 to the negative third. Notice anytime you have a scientific notation number, the only numbers that are included in this portion are going to be significant. And so this one has 3. And 5.20 milliliters, it is present, so starting from the left, the 5, the 2, and the ending 0 are all significant. That also has 3. How you round your answer for mathematical operations involving scientific measurement? If you have an addition or subtraction rule, just remember that as you round your answer, The rounded result may have no more decimal places than the measure having the fewest. So here in this example, you'll notice the second number only goes to the 10th, so therefore you must round your answer to the 10th place. We're not counting number of significant digits, we're only looking at decimal places. The rule for multiplication and division, however, does involve the number of significant figures in the measurement. And so you'll notice as you multiply this series of three measurements together, the first one has 3, the second one has 3, the third one only has 2. Therefore, you must round your answer to 2 significant digits. And you'll notice that 502.392, the only way you can write 500 and have 2 significant figures is in scientific notation, because if you write it like this, well, first off, you can't write it 502 because that's 3 sig figs. You can't just drop it and call it 500 because that's only 1 sig fig. If you write it 500 with a decimal, then it's 3 again. So the only way you can properly write this in scientific notation with 2 significant digits of 5.0 times 10 to the second. Okay, let's practice doing some math operations and rounding our answer. If we add those 3 measurements, your calculator is going to spit out 79.15. The unit is meters. Okay, and so in looking at this addition, recalling that the rule states you can have no more decimal places than the measure having the fewest, both the first and the third measures only go to the 10th place, so therefore we're limited to the tenths. How do I write this number? Accurate to the tenths. 79.2 meters. Okay, the second one, we have to add 1.52 centimeters and 0.38 centimeters. When you do this in your calculator, it's going to spit out 1.9. Okay, however, you'll notice that both measures are accurate to the 100th of a centimeter. And so you have to take that into account for your final answer. So it also has to go to the 100th. So you must add a 0 at the end. The unit is centimeters. That doesn't change the value of the measure. It just tells you how accurately it was taken. For letter C, if you subtract 7.626 and you subtract 5 from it, your calculator is going to spit out 2.626. Okay, and once again, we're limited to 1 decimal because 5.0 only has the 10th place. So the answer must be 2.6, the unit grams. Okay, looking at letter D, this is the first one that has multiplication. If you take 7.55 meters times 0.70 meters, your calculator is going to report 5.285. Okay, so we're limited to 2 sig figs because 0.70 has only 2 sig figs. So you must round this to 5.3. The units are going to be meters squared. In letter E, same thing, you multiply these 2 digits together. Your calculator is going to report 4.1745. Okay, and notice that they both have 3 significant figures, so you must round your answer to 3. 4.17, the unit centimeters squared. And then finally in F, this is a division problem. You divide 2.452 by 8.4 cubic centimeters, and your calculator is going to reply this number, 0.2919044762. Okay, we're limited to 2 sig figs because of the number 8.4. How do I round this to 2? 0.29, the units, grams per cubic centimeter. That's really a density problem. On all these problems, you must show your work and you must use the factor label method or dimensional analysis, whatever you want to call it. I realize there are some of you that are adept enough to just simply know you can move the decimal to the left or right and change the value of this number. However, I want you to use dimensional analysis because in the future, you won't be able to do this when you're converting grams, moles, and atoms. It's not that simple. And so anyway, how many meters are in 7,526 millimeters? Well, as always, we need to start with what we know. 7,526 millimeters. If I want to convert this to meters, okay, I have to know the relationship between millimeters and meters. Well, I want millimeters on the bottom so they cancel. Meters will go in the numerator. I always give the larger measure the unit of 1. And so because meters are larger than millimeters, I have 1 meter, and the prefix milli means 1/1000th. And so 1,000 millimeters and 1 meter are the exact same thing. This is going to enable me to cancel millimeters, and be left with the unit meters. So if I take 7,526 and divide by 1,000, I get 7.526 meters. This problem is very similar to the last one. The only difference is we're going from kilo all the way down to milli. You may be astute enough to realize that, okay, kilo is 1,000 times larger than the base unit, and the base unit is 1,000 times larger than milli. And so between milli and kilo, there are 1 million units difference. But you don't have to really know that. You can always take this in smaller steps. And so let's do it that way. All right, so what do I know? Well, 4.25 kilograms, and I can convert this down to grams. Okay, I know kilograms is going to go on the bottom, and because kilograms is the larger of the two, I'm going to put 1 kilogram is 1,000 grams. All right, and now I can get rid of grams because I know 1 gram is 1,000 milligrams. Grams cancel, and now I have the units in milligrams. If I take 4.25 times 1,000 times 1,000, you're going to get 4,250,000 milligrams. Okay, it's also very important to note you cannot put a decimal at the end of 4.25 million, because then it makes all those zeros significant. You're limited to 3 sig figs due to the initial measurement in the problem. Okay, a rectangular fish tank has a volume of 12,500 cubic centimeters, and it wants to know how many liters of water it can hold. Well, the first part of this problem is you have to know the relationship between cubic centimeters and milliliters. 1 cubic centimeter and a milliliter are the exact same measure. So with that in mind, 12,500 centimeters cubed, well, I know that 1 cubic centimeter is 1 milliliter. That gets rid of cubic centimeters. And now I know that for every 1 liter, there are 1,000 milliliters. Milliliters cancel. I go ahead and I multiply 12,500 times 1 times 1. I'm going to divide it by 1,000. You're going to get 12.5 liters. Anytime you have a percent error problem, the beautiful part about this is because in the numerator, okay, I have the accepted minus the measured. Because this is an absolute value, it doesn't matter in which order that I subtract them, because really it doesn't matter if it's positive or negative, because really what it's looking for is the distance between these two measurements on a number line. And so what I always tend to do, and in this case it's going to be the same, but what I will do is I'll take 2.50 minus 2.38, and the absolute value of that, and it was positive anyway, is going to be 0.12, and this is liters. Now when I go and divide it by the accepted, well, what your answer should have been was 2.50 liters. The liters are going to cancel, times 100. If I divide this out, you're going to get, and then multiply by 100, 4.8% is your percent error.